Oh, mirror. Okay, great.
And speaking to the mic. All right. Hi, everyone. My name is Vasu. I'm going to be presenting jointly with Sam. We're both PhD students at Carnegie Mellon. And today we'll be talking about large language models for executable tax code generation. So let's start off with some motivation. I'm sure as many of us attended the interview in the morning, large language models have been starting to be used for a wide variety of tasks and reasoning tasks. One such example is tax code reasoning. So I took this screenshot from like over a year and a half ago now for when GPT-4 was first released. And one of the kind of demo examples that they want to highlight was the user was instructing GPT-4 in the playground that they're called Tax GPT, a large language model trained by OpenAI that is fed in the entire US tax code. And they are given a particular scenario. Alice and Bob got married and are filing jointly, et cetera. And it's asked to calculate their standard deduction for 2018. So this was, LLMs for legal reasoning, it's getting more and more popular, but obviously, as we've talked about, there can be problems where LLMs can hallucinate. And as Matthew mentioned initially, this can be a big problem for legal reasoning. So here I've included an example for Alice and Bob filing taxes jointly for 2025 and asking this standard deduction calculation. And if you were to prompt Claude, which is a popular off-the-shelf model, to break this down step by step and reference all the US tax codes that have been provided, it will actually end up with the incorrect answer because in one of the steps it forgot to take the correct number for filing jointly. It took the individual standard deduction. So LLMs can hallucinate with these, incorrect mathematical computations or fetching the wrong number, fetching the wrong information for these reasoning tasks, which is why LLMs have also been used to generate code to solve a lot of these issues. And one such example of a programming language in the legal domain is Catala. So Catala is a DSL for formalizing legal documents. I'm sure many of us have used Catala in this room, and we actually later on have another talk that does concolic testing for Catala. But the general premise for Catala, it has a very unique syntax and semantics that's kind of designed with encoding legal documents in mind. So here I have a very basic example of a scope, which is similar to a function in another language for calculating income tax. And in this case, we initially define income tax as our gross income minus deductions. But Catala has a very nice feature called exceptions that you can write later on in your Catala file that can essentially override the rule that you originally defined. And we're going to refer to these types of features as idioms, and Sam will talk more about idioms later in the talk. So in this case, our exception will check the condition that the individual's income is less than $10,000, and if so, the tax computation will return 0. So naturally, we asked, can we use large language models to generate Catala code directly as a way of performing these tax code executions? Instead of rather using the LLM as the reasoning model and calculator itself. And what we found, so we performed a variety of prompting strategies and studied 3 different popular off-the-shelf models. And we specifically looked at the statutory reasoning assessment dataset, or the SARA dataset, which has a lot of these sections of the IRS tax code and associated tax cases to sort of test these different scenarios of each section. And somewhat unsurprisingly, we found that the LLMs often produce syntactically and semantically invalid Catala. So as I showed before, Catala is a very unique syntax, and we also kind of jokingly refer to Catala as a no-resource language, in quotes. You may have heard of low-resource languages like Rust and other things in which there aren't that many examples on the internet. Catala has a magnitude fewer amount of examples on the internet, which means that LLMs have not really been trained on the syntax and semantics. And we can kind of summarize our results with all of our prompting different strategies with this plot where we see this, in the land of programming languages, Python, Java, C#, Go, LLMs can perform pretty well, both in producing syntactically and semantically valid code. But we found sort of the opposite side of the spectrum with Catala. And we generally observe that all these different prompting strategies like few-shot prompting, including a few examples, or self-debugging, allowing the compiler to return an error message and reprompting the LLM, or providing better documentation in the context window, overall improve the syntactic validity of the LLM-produced Catala code, but didn't really change the semantics that much. And throughout this experience, we also worked a bit more with Catala. We're not experts by any means, but we tried to sort of manually translate a lot of these sections of the tax code into valid Catala programs. And we noticed a lot of observations as well as observations in the LLM outputs. So in particular, one thing that we kind of struggled with was how natural language has a lot of implicit context, especially in the tax code. So I've included a small snippet here from section 63 about taxable income. And in this case, I'm showing the same example where gross income minus deductions allowed by this chapter would be the taxable income. And in Catala, you sort of need to declare all the metadata for your scopes, essentially the structure, all the inputs and outputs, before actually defining how that scope is calculated. So in this case, we've sort of hard-coded all of the inputs that we need in order to calculate taxable income, which includes gross income, standard deduction, personal exemptions, itemized deductions, etc. And then the issue here is that the deductions allowed by this chapter could be defined in a different section. In this case, it's in section 151, that we would need to essentially modify how we defined our metadata from before later on when we actually translate section 151 into Catala. So with that, I'll hand this over to Sam, who will talk about sort of more of our observations and what our approach to kind of solving this implicit context example is.
Yeah, so there's nothing in particular wrong with this translation just by itself. It's fine. It makes sense. It's correct in a certain way. The problem is in how we're able to use it. So the SARA dataset also provides a bunch of test cases. And so this would be an example. So you provide some information about some fictional people and data about them and their income and things like this, their situations. And you want to translate this into a way that you can actually invoke the Catala code that you've written, right? And as you remember here, this scope has a whole bunch of inputs, and then it has this output, which is the taxable income. So it assumes that you've already calculated all these particular inputs, and you provide it to the Catala code. And so that's fine. It works in this case. There's no problem. But what if you were provided some different information, right? What if you were provided, instead of these are the deductions that we've already calculated, what if you were provided oh, Alice and Bob have been married this long, and then there's this other information that you could use in theory to plug into some other section of the tax code. In this case, it's a bit more unclear, right? And so this isn't that hard to do in this particular example. What you would do is you would go look up the other sections of the tax code that are relevant to this data, and then you would call those scopes, and then you would use the outputs of those scopes as inputs to the scopes. But that's a little bit weird that you have to do that, right? Because I thought that the whole point of trying to translate this into a programming language is that it should be able to calculate it from the information that we give it. But then now when we're translating the test case, we have to translate all this sort of plumbing and connecting functions together in the test case itself. So there's a lot of limitations in how you can actually what you can do given a Catala function, and having to write this plumbing information yourself introduces a lot of room for error and a lot of extra complexity. So we did a couple of little experiments, and these aren't nearly production grade. These aren't even anywhere near to the level of sophistication as Catala, but they kind of suggest a couple interesting ideas that we want to hear the thoughts from this community on. So rather than thinking about this as a function in the standard functional programming sense, we could think about it as a computation graph. So here we have like the gross income, we have the deductions, we have the taxable income. And maybe some of these nodes could also be computed from other nodes in the graph. Like you can see there's an arrow that kind of goes off screen. Like if you have the deductions in hand, you can use that. And if you don't, then you could compute it from something else. And the graph, the structure of the computation graph says how to compute things from other things, regardless of which things you actually have. Like as long as you have enough, it can compute what you want. So we designed a domain-specific language. This happens to be embedded in Clojure, which is a Lisp, but that doesn't really matter too much. It was just easy to prototype. And so the way that we define computations in what we call Dagger is you declare nodes in the graph. So like gross income, deductions, taxable income. And then you can define ways to compute those nodes from other nodes. So in this case, you can say, if you don't know what someone's taxable income for a given year is, you can compute that by subtracting the deductions from their gross income. And there's a couple things that are nice here. So one thing that is that this kind of looks just like saying like if gross income and deductions were variables, kind of like what they were for the Catala example, this code looks roughly the same. But if they're not provided as input, and if instead you provided data that you could use to compute gross income and deductions, it will instead compute them. It will see that they're not already present in the computation graph, and it will compute them. And it will pass down implicitly the context of, I'm talking about a particular year and a particular person, to these sub-computations here. So this question mark operator automatically passes down all the context that's shared between the node you're currently at and the node that you're trying to compute. So the code just looks natural, and this implicit context is only present in these declare directives here and not actually in the definitions. So the structure of the code mirrors more closely the structure of the original prose, despite allowing more flexibility in how it's used. So this is kind of like, this computation graph is like changing the paradigm from like functional programming to this like computation graph idea, incremental computation. There's like a lot of people who have done work on this before, like Adapton and Salsa are a couple examples if you want to look those up separately. But the nice thing is that we're also able to retain, we talked about idioms before. Catala has these useful idioms like conditions and exceptions, things that are common in like legal prose. And we're able to retain those as well. So we call them cases instead of exceptions, but it's the same idea. We could call this exceptions instead. And in Dagger, you're able to say, like, if this function returns true, then like for this rule, we return a different value. So the idea here is like essentially, yeah, I'll kind of skip over this slide because we don't have a lot of time. But the idea here is essentially like by changing the paradigm to like a different way that matches like this legal code more closely, but retaining some of the axioms, some of the idioms that we already know are useful from Catala, can we make a language that's more straightforward for humans to write and translate legal prose, and also closer to the legal prose itself, so that large language models have an easier time doing it as well. And we don't have a sophisticated evaluation here. This is kind of early stage work, but yeah, that's pretty much all we have. Plug for Rohan's talk later this week, which is on like a similar idea of like, can we get the LLMs to like, do the reasoning yourself? So definitely come check out that talk on Thursday. And yeah, that's pretty much all we got.